Let's state two theorems together with their proofs. Theorem. Suppose some set is orthogonal. Then that set is also linearly independent. And in particular, it forms a subspace. Sorry, I mean to say it forms a basis of some subspace. How do we know that? Well, by the definition of independence, if this set is linearly independent, then the only way for this combination to be zero is if all of the coefficients are zero. So let's say we have this set equal to zero. Let's take a dot product. In particular, let's take both sides of this equation and dot product it with u sub 1. Well, on the right, that will just give you 0. Any vector dotted with the 0 vector is 0. Over on the left, this dot product is going to distribute over this addition. And this up dot u1 will be 0. U sub p minus 1 dot u1 will be 0. And so on down the line. u2 dot u1 will be 0. So the only thing that's going to survive is u1 dot u1. Sorry, that's not the 0 vector. It's the real number, 0. Well, u1 dot u1 is not 0. We are assuming, and we shouldn't assume, we should write everything down properly, that these vectors are not the 0 vector. And only the 0 vector can be dotted with itself to give 0. So the 0 product property, you're multiplying two numbers together. Their product is 0. One of the numbers isn't 0. So the other number must be. If you used u sub 2 up here, you'd have gotten this same thing, except with c sub 2 and u sub 2. And the exact same argument would tell you that C sub 2 equals 0, and so on down the line. Contrary to what I said at the beginning of the recording, let's end this here, and the next theorem can be its own video.